Okay, so let's start. Hello, everybody, and a very warm welcome at the Extremal and Probabilistic Extremal Combinatoric Seminar, the webinar. Before I introduce our speaker today, let me remind you that this webinar is being recorded and it will be put on YouTube afterwards. So bear this in mind when you are asking questions. Also, I would ask you to avoid background noise, to mute yourself unless you are talking. Regarding questions, you are more than welcome to just unmute yourself and ask your questions, or if this is uncomfortable or for a technical reason impossible for you, you can use the chat and then I will stop the speaker and raise your question. After the talk, there is a normal question session. And after this question session, I also stop the recording. And if there is interest, we can have an informal talk, just some more crazy question or just anything. Okay, so it is my pleasure to introduce Istvan Tomon from ETH Zurich, and he will speak about Ramsey properties of string graphs. So you have the word.
Okay, so thanks everyone for joining. Yes, I will talk about some Ramsey type properties of string graphs. Before I tell you what string graphs are, let me talk a bit about Ramsey theory and the Erdős-Hajnal conjecture. So I'm pretty sure you all know what Ramsey's theorem is. So it says that if you have a graph on vertices and we ask that how large is the size of the largest clique or independent set, then this quantity goes to infinity as n tends to infinity. So the first quantity version of this was proved by Erdős and Sharir, who showed that if G is a graph on n vertices, then it always contains either a clique or independent set of logarithmic size. So later, Erdős showed that this bound is actually the best possible up to the constant factor. So his famous argument is that if we consider a random graph in which each edge is chosen independently with probability half, then this graph only contains logarithmic size cliques and independent sets with very high probability. So now we have this nice matching probabilistic upper bound, but one might wonder whether we can also find deterministic constructions having similarly good Ramsey properties. So now this question turned out to be very difficult. So even today, we don't know any deterministic constructions that have these good Ramsey properties. And this led people to believe that graphs that only have logarithmic sized cliques and independent sets must be inherently random-like in certain sense. So saying this the other way around, we can say that if we have some graph that possesses some sort of structure, say it comes from some geometric consideration or it avoids some small induced subgraph, then we expect such graphs to have much larger cliques and independent sets. And one of the most famous results supporting this is the theorem of Erdős and Hajnal. So what this theorem says is that, okay, let's just consider some graph which avoids some small fixed induced subgraph H. Then this graph contains either a clique or independent set of size e to the constant square root log n, where this constant only depends on this forbidden induced subgraph H. Then Erdős and Hajnal conjecture that actually this bound should be improved. So they conjecture that this e to the constant square root log n can be replaced with n to some constant. So instead of finding cliques or independent sets of size e to the constant square root log n, we should be able to find polynomial cliques or independent sets in such graphs. And so this is the notorious So in particular, this conjecture has been only verified for some very special graph H. So it has been verified for some small graphs, so every graph up to 4 vertices. And it also holds for some other graphs, which we can get through some graph operations using these small graphs. And in particular, until recently, it was open for the 5 cycle and the pass of length 4. So now this case of cycle of length 5 was especially notorious. So people believe that once you might be able to solve this, then you can prove the Erdős-Hajnal conjecture. So unfortunately, this turns out to be not the case. So a few months ago, this notorious case of the C5 was solved by Chudnovsky, Scott, Seymour, and Spirkl. However, their proof really only gives the C5, so the case of the pass of length 4 is still open. But in this talk, I want to consider the Erdős-Hajnal conjecture in a geometric setting. And I want to talk about graphs that are not necessarily defined by some small forbidden induced subgraph. So let me give you some notion which lets me do this. So we're going to say that a family of graphs G has the Erdős-Hajnal property if there exists some constant depending only on the family, such that every member of this family contains either a clique or an independent set of size, the number of vertices to this constant. Now, using this notion, we have the following equivalent formulation of the Erdős-Hajnal conjecture. So let's G be some hereditary family of graphs. So this means that G is closed undertaking into subgraphs. So now if this is not the family of all graphs, meaning that we have at least one graph which is not in this family, meaning that no graph in this family contains this one graph as an induced subgraph. So now if we have such a family, then this has the Erdős-Hajnal property. So now it can be easily seen that this conjecture is equivalent to the original Erdős-Hajnal conjecture, but I prefer this formulation a bit more because this again lets us study the Erdős-Hajnal property as those families which are not necessarily given by some forbidden induced subgraph, but let's say some families that arise from geometric consideration. And so in particular, I will consider the Erdős-Hajnal property of intersection graphs. So what are intersection graphs? So let's say we are given some family of geometric objects. And when I say geometric objects, at first you can think of very simple things like rectangles, line segments, convex, and so on. So now if we have a bunch of these geometric objects, then we can define their intersection graph where, so the vertices of this graph correspond to the elements of F, and two vertices are joined by an edge if the corresponding sets have a non-empty intersection. So it's a pretty straightforward definition. And so when we consider the Erdős-Hajnal property of intersection graphs, this has some nice geometric meaning. So we are asking the question, if we are given a bunch of geometric objects, can we select a large subcollection in which either any two objects have a non-empty intersection or any two objects are disjoint? And one of the first such results was proved by Lerman, Matusek, Pach, and Radoicic, who already proved this pretty general statement about convex sets. So they proved that if we have an intersection graph of convex sets, then this graph has the Erdős-Hajnal, so these families have the Erdős-Hajnal property, and in particular, every such graph contains either a clique or independent set of size, at least n to the 1/5. And here it's open how good this exponent 1/5 is. Okay, so now we already have this pretty general result. So one might ask that how much can this be pushed, or in what kind of more general geometric objects can we consider for which we can prove these Erdős-Hajnal type properties? And One interesting family of geometric objects to consider is the family of curves. So what's a curve? Curve is just the image of some continuous function from an interval to the plane. So really the only condition we want from this function that it's continuous, so it can be self-intersecting and it can have any other properties. And then a string graph is just the intersection graph of curves in the plane. So why are we interested in string graph and why are they studied at all? So it turns out that if you have any collection of arcwise connected subsets of the plane, then their intersection graph is a string graph. So you can approximate any arcwise connected set arbitrarily closely by curves, and it can be easily shown that their intersection graphs are string graphs. So in particular, it might not be that obvious at first, but actually it's pretty easy to show that intersection graphs of convex sets are also string graphs, and intersection graphs of any reasonable geometric objects are string graphs as well. Because when we talk about geometric objects, like this is not something really well defined, but one of the kind of weakest geometric properties is connectedness. So one can view string graphs as this kind of most general intersection graphs. And then this question about the Erdős-Hajnal property of string graphs was first asked by Alon, Pach, Pinchasi, Radoicic and Sharir. So they proposed the conjecture that the family of string graphs has the Erdős-Hajnal property. So first, let's just do a sanity check that whether this can hold. So clearly, the family of string graphs is a hereditary family, but it is already not obvious that it is not the family of all graphs. So are there any graphs that cannot be realized as string graphs? And here is an example. So turns out that induced subdivisions of K5 are not string graphs, and roughly the reason for this is that K5 is not planar. So now at least we know that the family of string graphs is not the family of all graphs. So let's see what's known about their Erdős-Hajnal type properties. So already in this paper where it was proved that the intersection graphs of convex sets have the Erdős-Hajnal property, so their argument implies something a bit more general. So they proved that intersection graph of X monotone curves have the Erdős-Hajnal property. So now what are X monotone curves? So curve is X monotone if this function f is monotone in the X coordinate. And then later, so in the paper where the conjecture was proposed, it was proved that the family of semi-algebraic graphs of bounded complexity have the Erdős-Hajnal property. So now let me give a bit of an explanation for this. So graph is semi-algebraic of bounded complexity if the vertices of this graph are points in some bounded dimensional space, and the edges are defined by a bounded number of bounded degree polynomials. And so these graphs have the Erdős-Hajnal property where the exponent depends on this complexity. So now the reason this is relevant for us, so this roughly tells us that if we have geometric objects that can be defined algebraically, say disks or rectangles, segments, then again, these intersection graphs have the Erdős-Hajnal property. But for example, convex sets do not belong in this category. So now later, Fox and Pach proved that if you have a string graph on vertices, then it contains either a clique or independent set of size and to the constant over log n. So this is almost the Erdős-Hajnal property, but slightly bit weaker, and it's still a big improvement from this general bound of Erdős and Hajnal. So now later, Fox, Pach, and Todt proved that if we have an intersection graph of curves, and we also assume that any two curves intersect at most k times, where k is a fixed constant, then we have the Erdős-Hajnal property. But now the exponent will depend on this number k. And finally, what I will talk about today is that indeed the family of string graphs has the Erdős-Hajnal property. So in what follows, let me talk about the proof of this theorem. So first of all, how can we prove any kind of Erdős-Hajnal type properties or Erdős-Hajnal type results? So what kind of tools we have at our disposal? So it turns out that we don't have that many tools, which is not surprising, as we don't really know too much about the Erdős-Hajnal conjecture. But one of the tools that was really successfully used in the past several years is the so-called strong Erdős-Hajnal property. So the idea is to prove a kind of stronger property. And so what is this strong Erdős-Hajnal property? So now let's say that we have a family of graphs. Then this family has the strong Erdős-Hajnal property if every member of this family contains so either it contains a linear sized bi-clique or the complement of a linear sized bi-clique. When I say bi-clique, I always mean a complete balanced bipartite graph. So a complete bipartite graph with both vertex classes having the same size. So now again, the difference is now instead of wanting a polynomial sized clique or independent set, we want a linear sized bi-clique or its complement. And indeed, it turns out that in hereditary families, the strong Erdős-Hajnal property implies the Erdős-Hajnal property. And in general, the idea is that it should be much easier to find large bi-cliques than to find large cliques. But unfortunately, oftentimes this strong Erdős-Hajnal property is too strong. So in general, if you wonder whether the stronger conjecture is true that every family has the strong Erdős-Hajnal property, then this can be easily shown to be false. So for example, if you consider a family which avoids some small cycle, then you can just have standard probabilistic constructions showing that these families are far from having the strong Erdős-Hajnal property. But still, it turns out that if the family does have the strong Erdős-Hajnal property, then there are many ways to show that it really has. So we have better tools of showing that the family has the strong Erdős-Hajnal property. And to show you some examples, so I think one of the first appearances of this idea is this result about semi-algebraic graphs. So originally, the way they proved the Erdős-Hajnal property is that they proved this stronger property. Now later, Fox, Pach, and Todt proved that the intersection graph of convex sets have the strong Erdős-Hajnal property. So note that so the original proof for convex sets having the Erdős-Hajnal property uses completely different ideas. So this is an alternate proof of this result, which shows a bit more. So now then Fox, Pach, and Todt prove that if we have family of curves, and again, any two curves intersect at most k times, then this family has the strong Erdős-Hajnal property. But this stronger, this new idea of using the strong Erdős-Hajnal property not only appeared in geometry, it also finds its way in structural graph theory. So very short and very nice result of Buscat, Lagat, and Tomasi is that if we consider a graph which avoids some path of fixed length as an induced subgraph and the complement of the path as an induced subgraph, then these graphs also have the strong Erdős-Hajnal property. So later, Chudnovsky, Scott, Seymour, and Spirkl extended this to trees. And this result, in some sense, the most general. So actually, it turns out that if you have a family of graphs which are defined by a finite number of forbidden induced subgraphs, then in order to have any chance for the strong Erdős-Hajnal property to hold, you need to forbid both a tree and both the complement of a tree. Otherwise, you can just have this standard probabilistic construction showing that it's not true. So this result of Chudnovsky's Seymour and Spirkl is this if and only if statement. So you have the strong Erdős-Hajnal property if and only if you forbid the tree and its complement. And so one more interesting result is this, again, by the same group of people. So they proved that if we forbid every subdivision of a graph as an induced subgraph and the complements of every subdivision, then again, these families have the strong Erdős-Hajnal property. So now these results show that this idea is very powerful. So natural approach to attack this question about string graphs would be to show that the family of string graphs has the strong Erdős-Hajnal property. So unfortunately, this turns out to be false. So the family of string graphs do not have the strong Erdős-Hajnal property. And so let me give an explanation of these negative results while introducing some properties of string graphs. So it turns out that string graphs are very closely related to another family of graphs, the so-called incomparability graphs. So what's an incomparability graph? So let's say that we can define a partial ordering on our graph where we have an edge between two vertices if and only if they are comparable in this partial order. So now, if we can do that, then this graph is called a comparability graph, and the complement of a comparability graph is an incomparability graph. And the following nice result was proved by Lovász in the 80s. So he proved that if we have that a graph is an incomparability graph, if and only if it is the intersection graph of 0-1 curves. So now let me give a picture. So what are 0-1 curves? So let's say we have two vertical lines, and then if we have a curve whose left endpoint is on the left vertical line, right endpoint is the right vertical line, the curve is contained completely in this strip between the vertical lines, then these are 0-1 curves. And yeah, this result says that if we have such curves, then their intersection graph is an incomparability graph. And actually, one of the directions is easy to show. So let me just quickly show you that if we have an intersection graph of these curves, then this is an incomparability graph. So indeed, so if we have a bunch of 0-1 curves, then we can define a natural partial ordering on these curves. So namely, if we have this curve, this curve 4, say, then we can look at the area below it, and we can look at those curves that are completely contained below this 4. So in this picture, we have that these are 2 and 3. And so we say that one curve is bigger than the other curve if it is completely above it. Now, clearly, this will be a partial ordering. This can be very easily seen. And also, it is clear that if two curves are disjoint, then one is below the other. So this shows that the comparability graph given by partial ordering is the complement of the intersection graph of these curves. So the interesting part of Lovász's result is that the other direction also holds. So if we have an incomparability graph, then we can find curves that realize it as an intersection graph. So yeah, but why am I talking about this? So it turns out that incomparability graphs already do not have the strong Erdős-Hajnal property. And therefore, this implies that string graphs do not have it either. So in particular, Fox proved the following nice result about incomparability graphs. So he proved that if we have an incomparability graph on vertices, then either we can find a bi-clique of size n over log n, so almost linear, but not quite, or the complement of G contains a linear size bi-clique. And he also showed construction showing that these bounds are the best possible, so we cannot replace log n with anything else. So unfortunately, this slightly weaker version of the strong Erdős-Hajnal property already doesn't seem to be strong enough to imply the Erdős-Hajnal property. So we have to do something else. But let me mention that actually this relation between string graphs and incomparability graphs goes even deeper. So Fox and Pach proved that if we have a dense string graph, then it contains a dense incomparability graph. So now what this means that if we have a string graph on n vertices and it has some constant unsquared edges, then it contains some incomparability graph with some other constant times unsquared edges. And now it contains means that it contains it as a subgraph, so it is not necessarily induced anymore. And so the reason I mentioned this result is this: actually, in order to prove the Erdős-Hajnal property for string graphs, this result will be one of the key components. Okay, so now we know that we cannot use this strong Erdős-Hajnal property, so then how do we proceed? And now the idea is to let's maybe try to relax this notion of strong Erdős-Hajnal property. And therefore, I introduce this quasi-Erdős-Hajnal property. So now a family of graphs has this property if there exists some constant depending only on the family, such that the following holds. So now there will be a bit of a technical definition, but I will try to explain what this means. So now this family has this property: if for every G there exists some T. So now this T can depend on the graph G as well. And we can find these T disjoint subsets x1 up to xt of the vertices such that T and the sizes of these sets satisfy this inequality, whatever this means. And either we have that every xi is complete to every xj, meaning that every vertex of xj is connected to every vertex of xj, or there are no edges between any xi and any xj. So note that this is indeed a relaxation of the strong Erdős-Hajnal property, because it turns out that if you could choose t equals 2 every time, so if you are guaranteed to have t equals 2, then this is equivalent to the strong Erdős-Hajnal property. Because in this case, this inequality tells you that the sizes of x1 and x2 are linear, and then 1 corresponds to a complete bipartite graph and 2 corresponds to the complement of a complete bipartite graph. And so what we gain from this definition is that we allow this t to be much larger. And indeed, it turns out that the quasi-Erdős-Hajnal property not only implies the Erdős-Hajnal property, but they are actually equivalent in hereditary graph families. Okay, but now you might wonder that, okay, if we have this equivalent property, then what's the gain? So what do we win by considering the quasi-Erdős-Hajnal property instead of the Erdős-Hajnal property? So and the answer is that now we can consider so-called lopsided results. So what I will prove is that if I have a string graph and my string graph is dense, so if it has some constant unsquared edges, then 1 holds, so I can find these sets so that they are pairwise complete to each other. And if G is sufficiently sparse, then 2 holds. And in this case, I can actually guarantee t equals 2. So in this case, I find a linear size bi-clique in the complement. And here, sufficiently sparse means that there is some threshold density, so that if I am below this threshold density, then I am guaranteed to find this. And note that this is really the advantage of the quasi-Erdős-Hajnal property, because if you would try to prove something similar for the Erdős-Hajnal property, that's clearly false. So if you would try to show that dense graphs must contain large cliques, that's obviously false, and also similarly for sparse graphs. So this is the real advantage of this new property. And actually, this was also the advantage for all these strong Erdős-Hajnal proofs. So in every time the strong Erdős-Hajnal property was proved, then they proceeded in the same way. So they showed that if we have a dense graph, then we must find dense bi-clique, a bi-clique and we have a sparse graph, then we must find the complement of a bi-clique. Okay, so this is the plan, and now we have to prove two things. So now let me start by giving some outline of the first line. So we want to show that if G is dense, then we can find these sets that are complete to each other. But note that I already had some statement about dense string graphs. So I already told you that every dense string graph contains a dense incomparability graph. So if I want to prove this statement for string graphs, it's actually enough to prove this statement about incomparability graphs, which are obviously seem to be much simpler to handle. And this is indeed what we are going to prove. So basically, my main contribution to the proof will be the following lemma. So I prove that if G is an incomparability graph on vertices, then I can find T and these T disjoint subsets such that they satisfy this inequality as the one I need in the definition, and xi is complete to xj for every ij. So in particular, this lemma will follow from another general lemma, which I will just refer to as a bipartite lemma. So this will be a lemma just about bipartite graphs without any additional conditions. So hopefully this lemma might be usable in some other general settings. So now this bipartite lemma says the following. So let's say that we have some balanced bipartite graph, both vertex classes have size m. Then at least one of the three conditions will hold. So either the maximum degree of G is linear, or there exists some A prime in A, B prime in B, such that A prime and B prime are both linear, and there are no edges between A prime and B prime. Or there exists T, at least two, and T vertices A1 up to AT in A, and T sets X1 up to XT in B, such that this set Xi is contained in the neighborhood of AI, but Xj is disjoint from the neighborhood of AI, and I have this same inequality as here. So again, this bit in a few seconds, I will show you a picture which helps to clear us this third part, which is the most technical. But so let me talk about how this lemma, how roughly this lemma implies this lemma. So I will apply this bipartite lemma to a comparability graph. So I will apply this to the complement of the incomparability graph. So now I will have some comparability graph, and so I can take just some linear extension of the underlying partial ordering, and I can just cut the graph in half with respect to this linear ordering. This gives some bipartite graph. And now if I have this large maximum degree, so this first part will correspond to roughly the statement that this comparability graph is dense, or in other words, that this comparability graph is too sparse. Now this second condition will correspond to the statement that I can find two sets, so I can choose T equals 2, and I can find two sets which satisfy this condition. And the third statement will correspond to this statement in general. So let me show you a picture of why this is true. So let's assume that the third case holds. So that's the most interesting one. Then it means that we get the following picture. So we have this bipartite graph AB. So we found these vertices A1 up to AT. This sets X1 up to XT. So X1 is in the neighborhood of A1, X2 is in the neighborhood of A2, ... And but A1 has no neighbor in X2, and A2 has no neighbor in XT, so on. So now I claim that if this is a comparability graph and A comes before B in the partial ordering, then this implies that there cannot be edges between X1 this xt, which means that in the incomparability graph, they are complete to each other. Why is this true? So suppose this is not the case, so suppose there is some edge between x1 and x2, say. Now we can assume that in the partial ordering, the vertex in x2 is larger than the vertex in x1. And also that in this partial ordering, we can assume that this x1 is larger than a1. But now because we are in a partial ordering, we must have this edge as well because of the transitivity condition. So, but then this is a contradiction. So we must have that there are just no edges between. So this is roughly the implication. I don't really want to talk about the proof of this bipartite lemma because it's a bit technical. But let me mention that as this is just a lemma but bipartite graph, it actually finds some other applications as well in other Erdős-Hajnal type problems. So for example, with János Pach, we managed to show that if we look at an ordered graph, so we have a vertex ordering on our graph, and we forbid monotone paths and the complement of monotone paths, then again, these graphs have the Erdős-Hajnal property. So without the ordering, this is just the same as the result of Busquet, Lagot, and Thomas. And so we managed to show that even in this stronger setting with this ordering, this also holds. And again, the interesting aspect of this is that these families also do not have the strong Erdős-Hajnal property. So you needed to come up with some new technique. But more interestingly, it turns out that one of the key ideas on the proof of the case of C5 by Chudnovsky, Seymour and Spirkl, this also used some formulation of this bipartite lemma. Okay. So this is all I wanted to say about dense string graphs. So sorry, so to go back a little. So basically what I was showing you is that this first part of the theorem holds. So now let me show that the second part holds. So let me show that if G is sufficiently sparse, then I can find a linear sized bi-clique in the complement. So now actually I have basically nothing to do with the proof of this. So this almost immediately follows from a very nice result of Lee, which let me describe to you now. So this result of Lee is about separators in string graphs. So now what's a separator, or maybe known as a balanced separator? So if we have a graph, then separator is a subset of the vertices, such that if we remove this subset, then the graph not only becomes disconnected, but also it will not have large connected components. So every connected components of G minus S will have size at most 2/3 of the number of vertices. And so usually the existence of small separators is a very useful thing, because if your graph has a small separator and you want to solve some kind of problem on your graph, then this tells you that basically you can divide your problem into two smaller subproblems. So for example, if your graph has small separators, then this speeds up a lot of graph algorithms, and also it is very applicable in theoretical graph trees, so you can prove a lot of very strong properties of graphs that have small separators. And so maybe one of the most famous results about separators is the theorem of Lipton and Tarian, which says that planar graphs and vertices contain separators of size square root n. Now, building on this result, Fox and Pach proved that if we have an intersection graph of n curves, and G is the total number of crossings between these curves, then their intersection graph also contains a separator of size constant square root G. So unfortunately, if your string graph has many crossings, which can easily happen, then this statement doesn't really say anything. But then Matuszek proved that if we have a string graph with m edges, then G also has a separator of size constant square root m log m. And finally, very recently, they improved this to constant square root m, and for every range of parameters n and m, this bound is the best possible. So every string graph contains a separator of size square root m. So why is this useful for us? So now this result about separators immediately implies the following theorem, which we need. So if G is a sufficiently sparse string graph meaning that its density is below some fixed constant threshold, then the complement of G contains a linear sized bi-clique. So just let me show you a picture. So for example, here's a picture of 500 curves. Now this collection contains a small separator. So now if you consider these red curves, you remove them, then you can see that your collection of curves basically broke into two parts, and broke into two large, so two linear sized parts, and there are no edges between them. So in general, you can just, if you have more than two components, then you can just group your components together so that they both sides have linear side, and in the complement of graph, this exactly corresponds to a complete bi-clique, and this is exactly what we wanted. Okay, so let me mention that I could also prove this interesting result that here sufficiently sparse means exactly that the density is below 1/4. So it turns out that if we are slightly below 1/4, then we can find this linear sized bi-clique. But if we are above 1/4, then it might happen that we can only find logarithmic sized bi-cliques. So there is this really sharp threshold at 1/4. And the reason that 1/4 is kind of the right threshold is again that K5 is not planar, very, very roughly. Okay, and just to spell it out, so this implies that if G is a sparse string graph, then we can choose T equals 2, and I can find two disjoint sets, x1 and x2, such that this inequality we want is satisfied, and there are no edges between x1 and x2. So this proves the second part of our theorem. So in particular, we got that the family of string graphs has the Quasi-Erdös-Hajnal property, which then implies that the family of string graphs has the Erdős-Hajnal property. So this is basically all I wanted to say about the proof. Now let me finish my talk with one open question. So I proved that if we have a string graph and n vertices, then there exists some constancy, so it contains either a clique or independent set of size n to the c. So now it would be interesting to say something about the value of this constancy. So one could definitely calculate a specific constant from our proof, which I didn't do because unfortunately this constant depends on a lot of other constants coming from other papers that also didn't calculate constants. So it seemed like a waste of time doing this, but it would be probably very far from the truth. But on the other hand, the best known upper bound just comes from a construction of Kinchel. We showed that this constant is at most 0.405. But in particular, the construction of Kinchel only uses segments. So I think it would be really interesting to see some construction that really uses the full power of curves to get below this bound. And it would be just, and in general, it's just not easy to come up with any kind of construction of curves having these good Ramsey properties. So basically anything would be interesting. And so this is all I wanted to talk about. It was a bit faster than I expected. Sorry for that, but thank you for your attention.
No problem. Thank you very much, Istvan. May I suggest that we unmute ourselves and give Istvan a big applause for his very nice talk.
Thank you.
So if anyone has a question, yes, Nicholas? Oh, no, it's an applause.
So do you have any feeling where to expect this constancy? I mean, I understand that I'm not asking you for a particular value, but like, do you think it's really a lot below 0.4 or?
And I hope that it's below, just so there are really some interesting constructions. So because let me say that this construction is basically you find an explicit configuration with 160 segments, and then you can blow it up basically. So it would be interesting to. Usually these blow-ups never give you the right answer, so I hope that you can do something a bit more interesting.
I see.